Thank you so much for joining this lesson. We'll be continuing with the Physics Paper 2, the Kcse 2024 paper, in preparation for the Kcse 2025. Remember, the section 1 of this paper has already been uploaded, clearly discussed. So if you've not taken part, kindly find time and check section 1, paper 2, 2024 Kcse Physics. You will see everything properly analyzed. So now we are going directly to the section B, number 14. We're going to answer all the questions. Look at number 14. The figure shows an electromagnet setup, an electromagnet, whereby this is a magnetic field, which is going to cause another magnet and also some current to flow in the setup that you can see. So the question says, when the magnet is moved towards the coil, as you can see, according to the arrow, the milliammeter reads a maximum current of 0.1 milliamperes. Explain how the current is generated in the circuit. So we are supposed to know that actually most of the cases I'll be discussing, just make sure that you are keen in the discussion, because I cannot write everything. There is a lot of discussion in this paper actually. The paper 2 is not having a lot of calculations. So kindly bear with us. We will be talking much than the writing. So when the magnet is moved towards the coil, the magnetic field lines cut across the coil. Then now we say that a changing magnetic flux linkage is created. Then it causes the induced EMF that causes the current to flow. Therefore, we will have the magnetic field lines linking with the coils. So these are magnetic field lines from the magnet. They link up with the coils. Hence, an EMF is generated. The induced EMF is the one now which will lead to the flow of some current. So that is the point. Magnetic field links up with the coils in the turnings in the coils. Then an EMF is introduced or induced. The induced EMF is the one that leads to the flow of an induced current thereafter. Using the same setup, state how current can be increased. So we can increase the current. Remember, we are taught to use this setup. So there are very many factors that can lead to the increase of the current which is produced. One of them being using a stronger magnet. But now that we are supposed to use this setup without changing the apparatus, then we can talk about using a higher speed or moving in the magnet at a faster rate. Moving in the magnet at a faster rate. Moving in the magnet at a faster rate. That way, you will not have changed the setup at a faster rate. You know, we will have an increased rate of magnetic flux linkage, leading to a greater EMF and hence a greater current shall flow. On the figure, indicate with an arrow the direction of the induced current in the coil. Direction of the induced current. So remember, when according to we have what we call the Lenz's law. So according to the Lenz's law, we usually have the magnetism produced opposing the magnet producing the change. So we will have another north produced at that point. And when a north is produced, first of all, have we indicated? Yeah, indicate. Let's first indicate. So we will have a north, so that the change produced now is opposing the change producing it. So in other words, the magnet produced will have a pole, which is the same as the pole of the magnet at that particular end, so that the change produced opposes the change causing it according to Lenz's law. So this is how the current shall now flow. That's how the current will be flowing. Yeah, that way. Then we are supposed to explain now why the current flows in the direction that you've shown. And that's why I'm talking about the Lenz's law, whereby as the north pole of the magnet approaches the coil, a north pole is induced at that end of the coil to oppose the change that causes it. According to the Lenz's law, the current will hence flow in the anti-clockwise direction. So we will have current flowing in anti-clockwise direction because, and actually you don't even need now the Lenz's law. Once you've said that current flows like that, automatically when this one is a north, then we can use the right hand grip rule, or rather the clock rule, to say, according to this point, if you grasp it with your right hand such that your fingers point the direction of flow of current, then your thumb is going to show us the north. So as long as this is the north, and we know that a north is produced there, then we can come up with the direction of current. We can come up with the direction of current according to the grip rule or even the clock rule. Look at number 14b. A family observed that after purchasing a fridge, the monthly electricity bill increased by 2,000 Kenya shillings in a 30-day month, probably April or any other. Given that the cost of electricity per kilowatt hour, or rather per unit, is 4 Kenya shillings, and the fridge was used for 24 hours per day, determine the power rating of the fridge. Determine the power rating of the fridge. Then we are supposed to know that the cost of electricity is usually given by cost per unit, multiplied by the units, the number of units consumed. Now, how do we get the number of units consumed? It should be in kilowatt hours. So we convert the power to kilowatts, then we multiply by the number of hours used. Therefore, we will say the cost of 2,000 Kenya shillings is coming from 4. Then 4 is multiplied by the kilowatts, which is the number of units, or rather the power, times the time it was used, which is now going to be 24 hours multiplied by 30 complete days. So we can get the kilowatt hours. The kilowatt hours, or rather the power. 2,000. Now this 2,000 should be divided by 4 times 24 multiplied by 30. This becomes 0.69444 recurring. So the power now is going to be, 0.6944 kilowatts, which can also be, watts is capital kilowatts, or when we multiply by 1,000 to make it watts, 694.4 watts. So that is the power rating of the fringe, which was purchased. Number 15 now, part 1. We are taught to state 3 uses of the electron gun in the cathode ray oscilloscope. So now in the cathode ray oscilloscope, which is also called the CRO, then the electron gun has several uses. We have the anode in it, we have the cathode in it, and we have the grid. So in the electron gun, we can say the grid controls. I'm just trying to be more specific. You can just talk about, you can actually go direct to the role and say that the gun, the electron gun controls the brightness on the screen. This is a simpler way of saying that it controls the intensity of the electron beam that strikes the screen. You know, when the grid is made more negative, or rather less positive, we have less bright. When it is made less negative, which is more positive, we will have a lot of them attracted, and hence a brighter spot will be observed at the screen. Therefore, the electron gun, which has a grid, the grid is yeah, that's how we write the grid, not grind, grid there. It controls the brightness at the screen. We also have anode, which is part of the gun. So anode attracts, and it also focuses the electron beam. The electron beam to the screen. It attracts and focuses the electron beam to the screen. We also have the cathode, which is part of the electron gun. The cathode produces, and let me adjust the screen, produces the electrons, or rather the cathode rays. Yeah, the cathode rays like that. We can look at Roman 2 of number 15. This is a very serious exam. Actually, when you observe the paper very keenly, you discover that it has very little calculations. Very little calculations. Very little calculations. Meaning that here in 2024, students were just required to account for physics, to deliver content. How much physics do you know? Huh? The physics itself now, not just memorizing a few formulas here and getting formula. No. This one, you're required to have some content. State the reason why the inner walls of the cathode ray oscilloscope is coated with graphite. We know that graphite is a good conductor of heat and electricity, of course. Therefore, there are several roles, and one of them is to prevent the tube or the CRO from external fields, external electric fields. From external electric fields. There are several roles. It can also be used for earthing, because if any electron strikes it, then it gets conducted away. So to earth, or rather conduct away any stray electrons that strike it. Yeah, any that strike it. And also, we are supposed to talk about this particular graphite layer assisting to accelerate. It accelerates electrons to the screen. Yeah, to the screen, since it has electrons which are negative, hence repelling the electrons produced at the cathode. Therefore, you find it works to ensure that the electron beam is repelled. And if repelled, then it will be not distracted towards the walls. It will be directly focused to the anode, rather to the screen. Look at part 3. Describe how a cathode ray oscilloscope can be used to measure voltage of a cell. This is one of the main uses of the CRO. So to explain these uses, the first thing, we connect the cell across the Y plates. Connect the cell across the Y plates, which are also called the vertical deflection plates. Then we adjust or set the Y gain using the Y gain knob, of course, to obtain a reasonable vertical displacement. Set the Y gain to a reasonable sensitivity or a reasonable vertical displacement. Then once you complete the switch, you can now determine voltage using the formula. Determine voltage using the formula, the Y gain setting, or rather the sensitivity times the displacement. V equals to vertical displacement times the Y gain setting. Yeah, the Y gain setting, that too. Let's look at figure 5, which shows an X-ray tube. And as we continue about the X-ray, kindly allow me bring to your attention a very interesting program here. Look at the name. We're calling it the one-term ahead program, whereby students and learners are going to study term 1 work of 2026 during the holiday from the 10th of November all the way to the 12th of December via Google Meet. Google Meet is a very serious platform whereby there is one-on-one interaction. It's just like a normal classroom, whereby you get to answer questions, you ask questions, you get taught serious content for the term 1 work. So we'll be covering term 1 work, term 1 content over the holiday. Please welcome, invite a friend. We are inviting the junior school students and also the senior school students for the programs. So thank you so much as you continue supporting our programs. Remember, our number is already attached. Please use it to seek clarity on what we are going to do over the holiday. Otherwise, join our thousands of students and followers to continue benefiting from Shifting Grades online school. Back to the paper now. Back to the paper. We can see the cathode, we can see tungsten metal. Then look at Roman 1 of this question. On the figure, show with an arrow, or rather arrows, 1, the direction of the electron beam in the tube, and 2, the direction of the X-rays produced. So you're supposed to know that electrons move after they have been produced at the cathode, of course, through thermionic emission. We'll have the electrons flowing to the negative There should be an arrow for the direction like that. It's beams of electrons moving. They're being attracted to the positive anode like that. Yeah, to the positive anode. Then something else. This is the beam of electron. Then something else that you're supposed to show is you see the tungsten is at an angle to ensure that once they strike there and some of the energy is converted to X-rays as the other becomes just heat energy and conducted away, we will have now the X-rays produced. We'll have the X-rays produced now coming out through the window. So this will be the X-rays produced now. Yeah, X-rays. So the X-rays produced shall come out, of course, through the window. So we usually have a window here. Yeah. We'll have a window there through which the produced X-rays now will flow out. So we are done with these particular parts. Now we can check something in the Roman 2 of the same. State two ways by which focusing the electron beam is achieved in the tube. One, we ensure that there exists a very big potential difference, very big one, potential difference between the anode and the cathode. Actually, they are connected to what we call an extra high tension. So one way of ensuring that the electron beam is attracted is the great or the big potential difference between the anode and the cathode. The anode and the cathode. Very simple. Between the anode and the cathode. That way, we will have a very serious attraction. Very serious attraction. Again, we can also talk about the shape of this particular cathode. Look at the shape of the cathode. It's concave in nature. So the concave cathode also participates in focusing the beam to the anode. Because alternatively, you can be asked a very interesting question. You're told to state the reason why the cathode is concave in shape. Why is it concave? To ensure that the produced beam of electrons is focused to the anode. So that is the main reason. Yeah, those are some of the ways of ensuring that the beam of electrons or the electron beam is attracted. Yeah. Number 16, part A, Roman 1. State the meaning of the term photoelectric emission, or rather photoemission, or rather photoelectric effect. It has all those names. Photoelectric emission is also called photoelectric effect, which is also called photoemission. And this is the process of dislodging. The process of emitting, or rather dislodging, emitting electrons from a metal surface, by irradiating it, or rather illuminating it using a light, or rather a radiation of sufficient energy. Sufficient energy, sufficient, you can say sufficient frequency. Yeah, sufficient frequency. You know, it's the frequency that contributes to what? To energy. So sufficient frequency, which in turn leads to sufficient energy. Remember, there is a level of frequency, which in turn is the energy, which you can focus on a certain metal, and photoemission does not occur, simply because every metal surface requires some minimum energy for it to cause photoemission. Therefore, the light which is being focused on the screen, or rather being focused on the metal surface, should be having sufficient energy, or rather sufficient frequency, because you know very well energy equals to HF, Planck's constant times the frequency. Yeah, Planck's constant times the frequency. Explain how the energy of a photon is used by the electrons during photoemission. Once the energy is absorbed, part of the energy, part of the energy which we call the work function in this case, is used to dislodge, or rather to emit electrons from the surface by breaking their attraction from what you call the nuclear attraction. They are usually attracted to the nucleus. So energy is used to break them from to break the forces of attraction. Then the remaining energy, is used by the electrons as the kinetic energy at which it flows with. Therefore, the electrons now are able to flow from the metal surface, because apart from the energy, or apart from the photon having energy enough to dislodge electrons, there remains extra energy, which now becomes kinetic energy to enable the electrons to flow. Then part B, explain the meaning of the term stopping voltage as used in photoelectric effect. This is the minimum voltage above which no photoelectric or no photoemission, no photoelectrons that can reach the anode. Yeah. The minimum voltage. The minimum voltage above which no photoelectrons can reach. No photoelectrons can reach the anode. No photoelectrons can reach the anode. Then part C now on the Einstein's equation of photoemission. This is what we are going to apply. The Einstein's equation of photoemission. We are told that when a certain metal surface is illuminated with a light of wavelength 4.0 times 10 to the power of -7 meters, it emits photoelectrons whose kinetic energy is 6.0 times 10 to the power of -20 joules. The Planck's constant has been given is 6.6 times 10 to the power of negative 34 joule seconds, and speed of light as 3.0 times 10, to the power of 10 meters per second. Determine part 1, the energy of the incident light. Energy of the incident light. We know that energy is usually given by Planck's constant times F, which can also be given by Planck's constant. Instead of F, we can use speed of light out of the wavelength, because we know that speed of light or any radiation is given by F lambda, meaning that F can be expressed as C out of lambda that way. So we can write Planck's constant times C out of lambda. So Planck's constant times 3.0 times 10 power 10, then out of 4.0 times 10 to the power of negative 7. So here we shall now have the energy of this radiation being equal to 4 after the computation, 4.9725 times 10 to the power of negative 19. Yeah, to the power of negative 19. These are joules since it is energy. So that's how we work out the first part. But look at the second part. At the second part, the question is, what is the work function of the metal? Remember, all the energy, according to the explanation that I've just given up there, all the energy is split into work function. Then the other energy becomes kinetic energy. Yeah? The other one becomes kinetic energy. Therefore, work function can now be obtained by total energy minus the kinetic energy through which the electrons flow at. Can see kinetic energy is given here, right? Therefore, for us to get work function, we need the total energy times 10 to the power of negative 19, then minus 6.6 times 10, let me check, times 10 to the power of negative 20. This is all energy, which is in joules. So this is going to give us 4.3125 times 10 to the power of 19 joules. So this is the work function of the metal. You should be understanding the Einstein's equation of photoemission. Very good one. Very, very good one. Number 17. Number 17, the question says, we explain how visible tracks of radiations are formed in the expansion cloud chamber when the most air in the chamber expands. So we're supposed to talk about now the moist air expanding. So the moist air expands. The moist air expands, causing cooling. And as the cooling occurs now, the radiation ionizes. The radiation ionizes. You know, all radiations have what we call ionization effect. Therefore, the radiation ionizes the moist air. The moist air forming ions. This is called the expansion cloud chamber. which is one of the mechanisms of what? Radiation detectors. Detectors of radiations, radioactive decay, in other words. Then now we say that water vapor condenses on the ions. Water vapor condenses on the ions, forming the visible tracks. Forming the visible tracks. So it's about the moist air expanding. Then as it cools, we will have the radiation now. We'll have the radiation, which causes ionization effect, ionizing the moist air, and it will form what you call ions. Now, upon these ions, we will have water vapor condensing on them. When vapor condenses on them, then visible tracks will be seen. And that's how radiation, or rather radioactive decay, shall be detected. Look at part B. The following equation shows a radioactive decay series. We have this can be uranium decaying to become thorium plus a certain radiation. State the name of the radiation emitted. So after the decay has occurred, the mass number and the atomic number before and after the radiation are supposed to be equal. Therefore, uranium 234.92 equals to 230 thorium, this is 90, plus unknown radiation. This unknown radiation should have a mass number such that when we add to 230, we should get 234. So that's 4. And also, on the other side, it should be having 2. So that when we add to 90, we get 92. In other words, the radiation, which has a mass number of 4 and an atomic number of 2, is helium particles. Helium particle, which is 42, and this simplifies to what we call alpha decay. So this stands for alpha decay. So it's an alpha decay. Very simple. Alpha decay. Look at Roman 2 of this, whereby we are told to state what would be observed on the leaf of a positively charged electroscope when the radiation identified in one passes close to the cap of the electroscope. When alpha decay passes near a positively charged electroscope, remember it's also positively charged. So alpha radiation has a very high, it has a high mass, leading to high ionization effect. So alpha radiation ionizes the air near the cap. Alpha radiations or radiation ionizes the air. I'm starting with the explanation actually. Above the electroscope cap, then positive charges leak away. Positive charges leak away simply because they are being repelled by the charges on the electroscope. Then now what will remain with negative? What will remain is the negative charges, which will attract most of the charges in the electroscope, leading to the collapsing of the electroscope leaf. Then we'll say that the leaf of the electroscope, the leaf of the electroscope decreases in divergence. Decreases in divergence. or rather, it collapses. Yeah, it collapses that way. Let's look at part C of this particular question. We are told that a certain radioactive substance has a half-life of 8 hours. 10 grams of the sample has an activity of 90 counts per minute. Determine the part 1 quantity of the sample that is active after 24 hours, or rather, what will be active is what has not decayed. The remainder, in other words. We know very well that the remaining, according to the decay equation, the remaining number is given by original number times half, and half is raised to small n, which is the number of half-lives. Therefore, the remaining mass shall be original, which is 8. Original mass is 10, sorry, not 8. So we shall write 10 times half, and half is raised to small letter n, the number of half-lives. So if one half-life is 8 hours, how many half-lives are in 24 hours? 24 over 8, which is just 3. That way. So 10 multiplied by 1 over 8. So 10 divided by 8 gives us 1.25 grams. Alternatively, we would have talked about originally having 10 grams. Then after the first 8, we go to 5 grams. After another 8 hours, we go to 2.5 grams. And finally, we go to 1.25 after another 8. All these 8s are adding up to 24 hours. Therefore, we can conclude that the remaining mass shall be 1.25. Yeah, 1.25 that way. Then look at part 2 of the same. Activity of the remaining sample after 24 hours. Remember, the original activity was 90 counts. So after 24 hours, it was 90. So it goes to, after 8 hours, we follow still the half-life. After the first 8 hours, we go to 45 counts. After another 8, we shall go to 22.5. And after the last 8 hours, we shall go to 11.25 counts per minute. Counts per minute. Remember, this can also be done using the formula, whereby we say the remaining counts shall be 90 times half multiplied by 3. Yeah, multiplied by 3. And this shall give us exactly 11.25 counts per minute. So that's it. The last question here is number 18. Look at part A of number 18. Use the energy band theory to explain why intrinsic semiconductors do not contact at absolute 0 temperature. Intrinsic semiconductors, these are pure semiconductors whereby nothing has been added to it, no impurity which has been added to boost the conductivity. Therefore, in these ones, there usually exists what we call a forbidden zone here, whereby between the valence band, we have valence band and a conduction band. Then we have the energy gap here, the energy gap at that point. Therefore, we have an empty conduction band, almost completely filled valence band. Therefore, electrons are supposed to cross through the forbidden gap into the conduction band. But now at room temperatures, the electrons are not having sufficient kinetic energy to move, as opposed to when heated a little bit. You know, when the semiconductors are heated, they conduct. When they are at room temperature or absolute zero temperature, their electrons, which are in the valence band, have very little energy, and therefore this type of conductors at absolute zero temperatures, they behave at what we call they are just non-conductors. Simply, they are non-conductors. But when heated up, they become conductors. So semiconductors are substances whose conductivity lie between that of conductors and non-conductors. So we can say that at room temperature, okay, not room temperature really, but you can say at absolute zero temperature. So let me use that language of absolute zero temperature. At absolute zero temperature, at absolute zero temperature, the electrons in the valence band, the electrons in the valence band do not have sufficient kinetic energy to make them move into the conduction band via the forbidden energy gap. Forbidden energy gap. Yeah, energy gap. So they do not conduct electricity. Yeah, they do not conduct electricity at absolute zero temperature. A very good question. Let's check part B. Figure 6 shows a PN junction diode connected to a source of EMF. We can see the N part. This is a PN junction. So the N part is connected to the negative. The P part is connected to the positive. Look at the first question. State the type of biasing shown in the figure. This is forward biasing. Forward biasing. Yeah, forward biasing. We're supposed to know that in forward biasing, the N part of the diode is connected to the negative part of the EMF. The P part of the junction is connected to the positive part of the external source of the EMF. Part 2, explain what happens to the charge carriers at the junction. So we should be able to say that the external electric potential is applied across the terminals. The external PD is applied across the terminals of the diode, making the charge carriers diffuse across the junctions. Making the charge carriers diffuse across the junction. The charge carriers diffuse across the junction. Across the PN junction, where electrons diffuse from N side. Electrons diffuse from the N side to the P side. Generating some current. or rather creating electron all pair movement. Generating electron hole convection current. Convection current. So current flows during forward biasing. Remember, during reverse biasing, the forbidden gap, okay, the junction will even widen the more. It shall widen the more. Then we are told now in this part 3, that is, we are told that in the space provided, sketch the current voltage graph for the diode in the figure. So when a diode is forward biased, then current voltage graph shall appear as we are sketching it here. So you have current in amperes, sometimes can be milliamperes, then the voltage in volts. This is how the graph shall be. Yeah, that's how it behaves. So you should be able to sketch such a curve. You should be able to refer to the KLB and see all the graphs under electronics. The figure 7 shows a waveform generated by an alternating current source, AC. So we can see the type of the curve. On the axis provided, sketch the waveform obtained when a PN junction diode is connected in the series with the source. We say that the work of a PN junction is to smoothen circuits. Therefore, this is what you'll be able to see. Yeah, that's what you'll be able to see. It can even be more. That's what you will be able to see. Then you are told to explain the shape. So we say that during the first half of the AC signal, during the first half of the alternating current signal, comma, the diode is forward biased and the diode is forward biased and allows current. Forward biased and allows current to flow. It allows current to flow. In the second half, the diode is reverse biased. In the second half, the diode is reverse biased, thus does not allow current to flow. Thus, no flow of current. So that is the section B of the paper 2 physics 2024 examination. A very good paper. I hope you shall invite your friends to this particular program to continue following. Remember to recharge airtime to your lines, Safaricom, Airtel, Telcom, by simply going to the Lipa na M-Pesa, the paybill number 737356, and the account number is the phone number that you're purchasing the airtime for. You enter the amount that you'd like to spend. Then after that, you can complete the transaction and your airtime shall be reflected instantly. So thank you so much for being around. See you next time. Thank you.